Okay, I didn't create like the new meeting, but okay, I guess we can start. Okay, this is lecture 3, right? Okay, this is 9. Oh, cute. Um, so basically, if you saw the announcement, I do post some office hours, which actually are after this class. But I also thought because after class, a lot of people just bring around to ask questions. I will try to more like 39, kind of like maybe 60, 70 minutes, so that there's still everyone who's kind of like some extra time stay here if they want to just talk about topics or maybe go over like a problem that I get over the assignment. Because like, maybe someone has to leave work and cannot stay for longer. I don't want someone to miss out on the conversation just because like they had to leave. So I'll try to kind of like do more like kind of like an hour long lectures, like plus or minus, depending on the day. But that way like everyone like because the point of like the class is just kind of like to explore what you're curious about, and if you end up talking to me, then I can get like a better sense. Oh, what you're more interested. Um, what I'm going to do today, I mean, I'll still say a little bit more about the tensor product and all this stuff, but I do feel like at some point I do have to give more like an official definition of what a tensor is. So I'm kind of like getting to that stuff today. And then maybe on Thursday, or depending on how much time you take us today, I'll start talking about the similar value decomposition because that's like a very useful tool for linear algebra, which will connect to like other stuff that we do with tensors and tensor networks. So it's kind of like useful to go over it. And it's like a very nice fun proof, like it gets like gives you like an excuse to review about stuff that you may have seen before about symmetric matrices, diagonalization, and all that stuff. So it's like a worthwhile proof, even if you have seen it before. So it's nice to have like a refresher. But yeah, I felt like okay, like at some point I do have to be more like a definition of what is like actually a tensor. So I thought I should probably focus on that today. But just as a reminder of what I was saying last time. So basically, again, I started very concretely, but then I'll kind of formalize some of this stuff in a moment. What I was telling you is that if you had two vectors, u and v, let's call them u1 and u2, and v, call them. Oh, in fact, let's do it a bit more general so that you see that they didn't have like to have like the same number of entries or anything like that. Um, if you think of them as matrices, right? Like this is like a 2 by 1 matrix. This is a 3 by 1 matrix. And if I ask you, okay, how can you arrange them in a way to multiply them as matrices, right? Well, in that, if both have the same number of entries, there are actually two possibilities. One gives you the dot product, right? And the other one will give you like the tensor product. But when they are of different sizes, that's actually only more reasonable way to do it. Because then you would flip, you, for example, could transpose this second one if you wanted, so you transpose it, and that gives you, a 1 by 3 matrix, right? And now if you kind of like stack them together, these two numbers match, right? And then you can do like the matrix multiplication. So kind of like the idea of the tensor product, is literally, I mean, in terms of like matrix notation, it corresponds to U times V transpose, right? Where if you write this all down, it gives you, U1, V1. It's really very easy to understand. You just do all the possible products that you could do, right? So you multiply U1 with all the possible entries of V, you multiply U2 with all the entries of V as well. So, and then, oh, sorry, this should have been V1. right? And this, well, in this case, would be like a 2 by 3 matrix, right? By the way, this is a good moment to bring this up. There is a convention, like when you're representing things like in this way, it is also common to just rewrite this, rearrange the entry so that it looks like a column vector. So if you want it, like this has six entries, and so you can just put, you choose like an order to, first, second, third, fourth, fifth, sixth. So another way to write this down, like it is less natural from our perspective because I started from like the matrix perspective. But if you only cared about the entries themselves and now how you're presenting them, it's also common to see it written as a column vector. So this is also written as, a vector with 6 entries. And when you do that, sometimes it is called like the vectorization of the matrix or a tensor. This would be like a more general operation where, where if you have like a matrix or a tensor, you rearrange the entries so that it looks like a vector. So this is called like a vectorization of the matrix. I mean, again, there's not like a unique way to do this, so it's not like a canonical thing to do. That's how like a mathematician would say it. But more like from a statistics or a data science perspective, if you just actually care about the numbers, like how you present them, maybe it's less important. So there you will see from time to time like the end result also represents like a column vector. But I kind of like it more from the matrix perspective. It's more useful for certain things. So I'll usually try to stick more with the matrix presentation unless explicitly I say let's look at the vectorization. Uh, so I like the idea. Um, what I was telling you last time is that this is a 2 by 2 matrix, but the point is that not every 2 by 3 matrix you can not for every 2 by 3 matrix you could find a vector U and B for which the matrix is just a dependent product of two vectors, right? So the point is that you know not every 2 by 3 matrix, let's call the matrix A, um, can be written in this form, right? Can be written um, that is related to the rank. Like, when you can do this, it's precisely related to the rank of the matrix. And one of the homework problems that is due kind of Saturday, I think, or like the end of the week, is about showing that in the matrix. I think I did it just for the square matrix, but but if the matrix is rank one, then you can find the vectors U and B that allows you to represent that way. It's like a fun exercise, but again, like that's also one of the reasons why I maybe want to finish after 1 hour that you think someone wants to speak about to discuss those problems. But kind of like idea, like whether you can do this or not is related to the rank. Okay, so this is related, whether this can be done, whether this is possible. Well, I was going to give you a few probability example about this, but before I do it, Okay, here's like a few probability example because I do want to show that this is connected to useful ideas of like independence, like statistics and other things like that. So here's like a very simple experiment. You don't even need to have taken probability theory to kind of like understand what's going to happen. So here's like a simple, like a nice example. So let's say you have two coins, right? So there are two coins, heads, tails, right? So there are four possible outcomes, right? Each has two possible outcomes, right? So like two times two is four, right? Like so all the four, like the two possibility, like the four possibilities would be uh heads, right? Heads, tails, tails, heads, right? And tails, right? And you may be maybe the points are fair or not, but there are if you were to do the experiment a couple like multiple times, like there's some statistics for how many times each of these outcomes occurs. So there's like what people call like a joint probability distribution, right? That tells you like kind of like summarizes all those possible probabilities, right? So you could say that this outcome occurs with probability P11. Okay, let's see what I'm going to, so I'm thinking of tails as heads as being the one. So let's say P12, right? Or like that's actually, oh my God, I should have called them 0, 1 or something like that. And then it would have been easier for me to kind of like, and let's see. Am I doing this consistently, like in terms of notation, or am I thinking? I'm thinking of well, I'm actually going to present it in a matrix soon, and that would clarify which one should have been which. So like you could have like let me do it like better first as a matrix. I should have started like that. You could put heads, tails. Let's say that this is for the and then yeah, like those are the possibilities. And I just want to use like the matrix notation, you know what I mean? So this is heads, tails. So heads, tails should have been P12, like if I want to be consistent here. And the other one would have been P21. Okay. Now that seems better. Tails, heads, you know, tails, right? And so the numbers, these numbers each of these numbers just represents like the probability that the corresponding outcome would occur, right? And then you could call this like the probability matrix or the joint probability matrix. That's probably like a better name, joint, because it refers to two things, two coins, right? So if you thought that the events, like that's what we would call this. If you thought that whether a coin lands heads or tails is independent, right, or whether the other coin lands heads or tails, right? If the events were independent, like if those two outcomes have nothing to do with one another, then there is a way to kind of like compute these probabilities for like independent events. And let me tell you how it goes. So like let me introduce two vectors, P and Q. So P I'll call P1, P2, and Q I'll call Q1, Q2. So kind of P is kind of like if you were only to do the experiment on the first coin, what are the probabilities? Of like the first coin lining of heads and tails, right? So these are like the probabilities for the first coin. And these are like the probabilities for the second coin. Probabilities. So yeah, if you have like this condition in statistics, which are the events are independent, like it, in the first case, it's kind of like easiest to understand that, right? Because if it's, there's like a 50% chance for each of them, right? 50% chance pass, 50% chance fails, 50-50, right? Like what you would expect each of them to be a quarter, right? Like one half times one half, one half times one half times one half, and one half times one half. But like yeah, in the case that the like the coins are like unrelated to one another, then these joint probabilities can be computed in terms of like the individual probabilities. So if the coins are independent of one another, then you would say, for example, the probability is multiplied for independent events. So you would say that P11 is P1 times Q1, and P12 is like P1 times Q2. I think that's, hopefully I'm using the notation in a consistent way, but yeah, I think I am, but so like the like the individual like the probabilities for the joint events are just the product of the individual probability. But if you were to notice that how these numbers come out, these numbers are just all the possible products of the individual probabilities, right? And that is literally what the tensor product does, right? So this is actually in the independent case, right? In this independent case, the probability matrix. So the probability matrix is just like the tensor product of those two probability vectors. So the probability matrix, or let's call it joint, to so the joint probability matrix P is the same as P tensor Q. So what that means is that if the probability matrix could not be written in this way, then that means that there is some connection in the outcomes of the coin. So they are correlated. So it's not what happens, like the outcome of one coin is not fully independent of the outcome of the other coin. And there is some connection between, the events are not independent. So if the matrix P could not be, if you were unable to express P as a tensor product, as a tensor product, then that means that the events are, what happens with what coin is not independent of what happens with the other coin. I mean, in biology, this would become more clear, maybe where like the probabilities are for genes, and then maybe like, genes are correlated. So maybe when one gene becomes active, there's like dominant, expression of a gene. So maybe, sometimes I think one gene that pushes the other one to become like activated, like they could come correlated. And so you could have like a massive, like, tensor, a tensor of like all the possible correlations between the appearances of a gene in a population. And then whether if they were like all independent of one another, then it would be just a massive tensor product of the individual probability vectors. So it is like a useful concept, like idea, like, where it is related to like this idea of like tensor product. I mean, in fact, like the tensor stuff, I mean, not that I know too much of the history of like how all of this was developed, but a lot of like the tensor techniques were actually developed like in mathematical biology and things like that for understanding population, genetics and things like that. Because this is like very important there, because you want to kind of like you come up with measures of relatedness between like populations, and like, for that we need statistical methods, and for that, like sometimes like it's convenient to have like this language of tensors. Um,
But then if we discuss like this,
mhm, mhm.
if there are dependencies, it can so you can go to them as some to.
Correct. Yes. Right. That's where I was headed next. So it is true, right? So definitely not every matrix can be written as a tensor product of this, but it can always be written as a sum. It can always be written as a sum of such tensor products. That's what I was going to say. Yeah.
Yeah, so just so like this one, so we're basically saying you have like sort of a problem. That's a problem. Not depending.
Right. So yes, but what is always true is that you can always at least find a sum of such independent factors. Yeah. Yes.
So it is related.
But right, it would be related to the rank. So that's what I was going to. Yes, like let me write it down now. Uh, okay. And so at least I'll give the definition of tensor rank. And next time, next time when I talk about on Thursday about the simple parallel composition, we'll see that this definition of tensor rank is the same definition of rank of a matrix. In the case of matrix happens to be like the tensor happens to be a matrix. So it would be a slightly different definition of rank that you have seen for matrices, but it will coincide, and that's kind of like you can see that in part because of the singular value decomposition. That is one of the reasons why I want to do that as well, because it's like which itself is like a very interesting result. So but yeah, just to give you like a quick example, but notice, you know just to go back to this case, like with the 2 and 3 entries, right? Well, let's actually do it for the 2 by 2 case. Okay, 2 by 2 case. So just so that I don't have to write so much notation. So, you have like the canonical vectors, like the basis vectors, E1 and E2, you know. I mean, hopefully someone worked it out over the weekend if you had a chance to look at the problems, but I mean, it's like super easy calculation. I don't mind doing it in front of you. It's not too bad to kind of like check explicitly, E1 tensor, E1 gives you 1, 0, 0, 0, right? E1 tensor, E2 gives you 0, 1, 0, 0. E2 tensor E1 gives you 0, 0, 1, 0, and E2 tensor E2, gives you 0, 0, 0, 1. If you do like the tensor products of those basis vectors, you get all those. There, four possibilities, and these are like the four possibilities. So it is very easy, like, if you have a random 2 by 2 matrix, right? Because of this, it's very easy to see that you can rewrite it as a sum, as a linear combination of these four ones, right? Because if you have like if you have like an arbitrary 2 by 2 matrix, A, B, C, D, then that is just like, A times 1, 0, 0, 0 plus B times 0, 1, 0, 0 plus C 0, 0, 1, 0 plus D 0, 0, 0, 1, right? So like what that tells you, like, again, this is E1, these are like the ones that I just did. So what that tells you is that any 2 by 2 matrix is a linear combination, any 2 by 2 matrix is a linear combination of individual tensor products, right? So, and this is, I'll write like the more general result in a moment, but this obviously happens like not just like for the 2 by 2 case, So any 2 by 2 matrix is a linear combination of tensor products but there you now the next thing that you notice is like, okay, but maybe this way of expressing it is not the most efficient one because I mean you chose this particular vectors, right? So maybe there is a matrix, that maybe okay, it's fine. It doesn't require a single tensor product, but maybe it just requires 2 or 3 tensor products instead of like the 4 ones. So that's where it becomes the idea of rank, because the rank is the minimum number of like, tensor products that linear combinations of tensor products that you need to write that matrix as a sum of tensor products. So the rank, so the rank in general, the rank of a matrix. Oh, let me say first, like in more generality. So like in general, for Rn, right? You could still have like the canonical basis, right? 100s up to En, right? Rn has dimension n. And so if you were to take all the possible tensor products here, then any n by n matrix, can be written as A equals the sum of Aij, Ei tensor Ej, kind of like in the same way as in here. So meaning that Ei tensor Ej equals a basis for that's the matrices of size n by n. But the idea is that this combination, like, may not be the most efficient one, because again, it is possible that you could find like as, different vectors that run trick. So the rank of A, so the rank of the matrix is, you could define as a minimum number R for which A is a combination of tensor products, for which A is a sum, from 1 equals, let's use a different letter so that it's not, confused. L equals 1 to R of like some constants. So you're just asking like how many summands, how many summands you need to use of tensor products to express the matrix as. And then minimum number is a rank. Yes.
Why?
No, I will prove it. Like again, once you have the singular value decomposition, you can see that this definition does match the usual definition that you know from like linear algebra. But yeah, like it isn't, it's a different, like this definition for rank is different from the one that you know of.
Well, I meant like, why is it that, right? It's the number that determines how many. At the other.
Well, no, that is, you mean the rank in the usual sense.
Yeah.
Yeah. No, it's like, right, like right now there are 2 ranks, right? Like, if that's what I'm trying to say. There's like the rank that you learned in 250, right? If that's where we learned rank for the first time. And then I'm coming up with this other definition for rank, right? Which is like, how many summands do you need, like, to express a matrix as a, as a linear combination of tensor products? What I'm saying is that, they're not like, I mean, if you're giving them the same thing, it's not like conspiracy, like it is because they are actually the same quantity, but it's not clear at all. I agree, like, so, but the proof is easier to understand if you do the similar value decomposition, which is why I want to talk about it. Because also like the SBD is like a little thing anyway for our course. But yeah, let me just say, leave it for next time. The next time, hopefully I'll get to why this coincides with the number of, with the rank, the number rank that you know from, linear algebra. So, if this were like a more formal course, I would kind of call this rank asterisk, just to say that, maybe this is like a different type of rank, but then the big theorem would be to say, rank asterisk is because there's a rank that you know of. But yeah, they are the same, but yeah, it's not clear at the moment, but so
let me just say it for next time. This definition of rank coincides with the one that you know from linear algebra. That's all I want to say. This definition with the rank that you know from linear algebra. Rank definition from linear algebra. The reason why I'm bringing this up is that because it is kind of like the definition that does generalize nicely to tensors of higher order. So if you have like, like I think I was also saying this like last time. So this definition is more useful for tensors with more indices. So for example, for this definition works better for tensors with more indices, more than two indices, right? So again, like, you could have like, I think we talked about that briefly the last time, like you could take the tensor product of three vectors, right? If you take the tensor product of three vectors, that gives you an order three tensor. This gives you an order three tensor. This is an order three tensor. And the definition, like again, to specify a tensor, if you think about it as a cube or the box, you just have to give the formula for all these entries. And all these entries are just all the possible multiplications you could do between like the individual entries of the vectors. So like the idea here is like the entry Tijk of the tensor is just the entry I of this vector times the entry J of this vector times the entry W of this vector. So you just do all the possible multiplications you could come up with. So this is just like Ui, Vj, Wk. Okay? But kind of like the idea is kind of like the same as what happens with matrices. Not every order three tensor is literally of this form, but everyone can be expressed in pieces of this, like of this type. So not every order three tensor is of the form, but not every order three tensor is of T can be expressed as U tensor V tensor W. And so the rank of an order three tensor would be what is the minimum number of tensor products that you have to use to express it this way. So the rank of T would be, let me use a different color. The rank of T is the minimum R needed for which like T, like it's a combination of like, I know, let's say C, let's use a letter L. UL tensor, VL tensor, WL. So, how many summons do you actually need? How many summons of tensor products do you need to reconstruct the tensor? The idea is that, in a sense, that kind of like the idea to have is that you know, the lower the rank, kind of like the less actual information it has, the more compressible it is. That's how you should think about it. So the lower, kind of like the rule of thumb is that the lower the rank, the more compressible, kind of like in a data science way, the tensor is, because there is less relation between like it becomes more independent, like the different parts of the object are more independent of one another, the more compressible T is.
You said not every order of tensor looks less than that.
Mhm.
If you're thinking about it like a matrix, where it can be like all in the non-square.
Oh, this also works for like even for right, like this also works for rectangular, right? Like so because you know that's why I started today with like the 2x3 case, right? You know, if you have like a vectors with 2 entries, vectors with 3 entries, like the matrices are 2x3, right? So not every 2x3 matrix literally is of this form, right? But kind of like the idea is like the rank of this matrix would be the minimum number of vectors that so yeah, doesn't matter. Like I'm sometimes focusing on the case where all the entries are the same number just because it's less notation needed. But yeah, there's nothing specific about whether the matrices or the tensors are cubical, you know, like squares versus like, you know, rectangular, like more like boxes. So it kind of like applies. It's a definition that applies well for like either different number of entries.
Other to like you know much you know.
I mean, there are partial algorithms depending on what you want to do. I mean, once we talk about tensor trains, that is like a tensor network. And kind of like there is an algorithm of sorts that, you know, to kind of build it up. But but kind of like in the matrix case, it is perfectly understood, you know, because that's like what the singular value decomposition gives you. It actually gives you the factors. That's how you should think about like this SVD from this perspective. But in the general tensor context, yeah, like the answer is less like it's more like I don't know, you know, you have to look at the particular problem you have in hand and to see what we can do. But but like but there are ways to kind of like approximate them because that's more like kind of the philosophy for a lot of this stuff, where you wouldn't be interested per se like in a exact answer because the exact answer, the idea is that what is the number of entries, like the number of entries of the tensor T, right? Is that they multiply, right? So it's the number of entries of U. Let's just write it like this. Is the number of entries of U, right? Times the number of entries of V times the number of entries of W, right? Because like you do all the possible multiplications, right? So the idea is like, if the tensor has like ordered, if the tensor has like multiple indices, this becomes like exponentially large, like, in a sense. And so you wouldn't be able to capture all of it because it's not, that's kind of like the perfect dimensionality type thing. So, but you do want to find a kind of like low rank approximation to like the tensor, which kind of like work for a lot of purposes. So that's more, and so since there are approximations, so you don't really necessarily think about finding the exact, what are the actual factors. But in some cases, there are conditions to kind of like, come up with algorithms to give exact answers, but not as great as in the matrix case. So the matrix case, that's where everything is perfectly understood. In the tensor case, there are still like really open conjectures about that, something like that.
Well, just to be clear, again, the reason if you want with the approximately you
Yes. Because even like I mean, here's like a very simple uh perspective, like imagine like everyone had like if every vector had n entries, right? So if every vector has n entries, then how many entries, like, would T required has n times n times n, like if it's order 3, right? Like just to make something concrete, then it would be n cubed entries, right? So if T has order 3, it requires n times n times n entries, right? And again, here's like the extreme case is like if the rank happens to just be 1, right? But you can see how it simplifies tremendously, because if the rank just happens to be 1, right? For example, if the rank of T is 1, so where like it's just like, a tensor product of three things, each one requires n entries, n entries, n entries. So if you were to store the entries, like, you only need to store three n entries, and then, you can reproduce any entry of the actual tensor just by doing that. If you were just interested in a particular entry of the tensor, you kind of locate like the entries of the individual pieces and do the multiplication, right? So each one would so this, each UVW would require n entries. So in terms of like storage, it requires. I mean, this looks weird, but it's just because the point of being rank one is that there are tons of correlation between the entries of T. That's why, there's redundancy, which is kind of like the point of the rank of a matrix, right? Like the point of the rank of a matrix is that the rows are not independent of one another, right? So information about row 3 is containing information about row 1 and 2, right? So that's when you go to Gauss-Jordan, right? Like that kind of gives you like the pure form of the matrix, in the sense like it has all the independent information that the matrix can give you, right? So that's why you end up with fewer entries in a sense than what you may have started with. So, but yeah, like and then and then like again in general, like like the tensor networks or things like that. The idea is like, if it had like 5 entries, I mean the tensor train, when we talk about this, um it would be kind of like instead of being n to the 5, it would be kind of like n cubed or something like that. Like the compression, like, so if you have a, which if n is large, that is a tremendous like gain, so. But yeah, like all of this has to be thought of the perspective that there's redundant information in the object, and so you want to get rid of the redundancy. Okay, and now to move to the like the official definition of a tensor, what a tensor like actually is defined as. Um, Notice here's like an interesting property that the tensor product has, which seems kind of silly, but it's actually very useful, which is that the tensor. Well, let me compare it with like just matrix multiplication. Okay, so observations, if you got a matrix and you multiply it by a vector, right? That operation is what people call linear, right? This is a linear operation because this is called like a linear operation in the sense, you know, if you replace the vector with a sum of vectors, right? Then you can just like do the individual matrix vector multiplications and add them together, right? And also that it pulls out scalars like nicely, right? So if you kind of like rescale the vector by a scalar, right? Like it's still, you can take it out, right? So that is like the more like abstract definition of a matrix, right? Like that a matrix is just like a linear transformation, which you may have seen before, right? So like the kind of like the grown-up version of definition of a matrix, right? So like so the generalization of a matrix is any operation between vector spaces, right? Which is linear, right? And that's why sometimes matrices are like all linear transformations, if you have seen that before.
which is, like, there are examples which, kind of fit this model, which are interesting, like, for example, like the derivative, right? Because if you remember, like, the derivative of a function, no, assuming the function has derivatives, obviously, we're not, no, like an example of this is like, if you remember like how the derivative of a function works, the derivative of the sum is the sum of derivatives, right? And the derivative of a constant times a function, right? Is just a constant times the derivative of the function, right? Which is why I imagine most of you already do differential equations, right? Sometimes we call linear derivatives or using this operator method, because the derivative is a linear transformation, right? So in a sense, it's like just like a generalization of a matrix. And if you choose a basis, then you can represent the derivative of the matrix, but in this side, in that case. But so kind of like there are many. All that I'm saying is that you can kind of like generalize the definition of a matrix to anything that's kind of like linear. And the tensor product is not linear, but it's what people call bilinear. So tensor product operation is bilinear. Okay, and that's what I want to emphasize here. So the tensor product, in fact, it's multilinear, but let me just start with bilinear part. It's bilinear in the following sense. That if you take like U1 plus U2 tensored V, I'll drop the arrows because it's becoming a bit too much. But if you were to do the tensor product between a sum and a vector V, that is the same as doing the individual tensor products. So that is the same as doing U1 tensor V plus U2 tensor V. Okay, so what we think about, the way we think about it is that it is linear in the first variable, but it's also linear in the second variable. That's where the word bilinear comes from, because it's linear in each variable. And so similarly, if you do U tensor V1 plus V2, that is the same as U tensor V1 plus U tensor V2. And same goes with scalar multiplication. If one of the factors you rescale by a constant, right? So if you were to do CU tensor V, that is the same as CU tensor V. And it doesn't matter where you put the scalar, like, So if you do U tensor CV, that's the same as C tensor U. C times U tensor V. So all that I'm saying is that the tensor operation, the tensor product, if you just replace one, if you replace one of the factors at a time with a linear combination, then you can split it up to like so it's called linear. So basically, you think about it as being linear in each factor. So it's more like that's what bilinear means. So it's linear in each factor. Thank you. Well, the thing is that in the case of the okay, so the thing is the difference is that in the case of the derivative, right? What is the input of the derivative? They are functions, right? And what makes it linear is that when you give the sum of two functions, it breaks it into the individual functions of the derivative, right? In the case of the tensor product, right? What is kind of like that domain, right? Like you're feeding kind of like
two pieces of two separate vectors, right? Like, like the first, like, because it is an operation kind of like, because some applications you need to give two things to multiply, right? So you have to feed two things into it, right? Let me just compare it. Like what I'm trying to say is that, okay, so like the derivative, let me just use a kind of like more function notation. What you have to give to it, right? Like the domain, you would say it's a function, right? And it produces two functions, right? Sorry, and it produces another function, right? But if you think of the tensor operation, right? The tensor product, the tensor multiplication, it is a multiplication, right? So it is like, it is a vector. Well, I mean, tensor a vector, or like just you can write it as comma vector, but that's fine. Well, and in this case, the way I was presenting it, it spits out a matrix, right? Because like the way I wrote it originally was a matrix. So here, because it has two factors, kind of like the next best thing you could ask for it is instead of like, like, you know, when you can add like kind of like add the factors, like, like you can add each factor separately because you have a vector here and I have a vector here. So you can do like a sum of vectors here or a sum of vectors here. And so what the tensor product is just asking is for like that to split into like for each of the pieces. But it doesn't make a lot of sense to kind of like try to ask it to, you know, to kind of like for the like a order paired plus an order paired vector. Like you can do it one at a time. So, but it's kind of like the natural generalization of being linear. It's just linear on each of the things that you have to fit into it. It's- it is not just like it is not like a linear transformation in the sense that like in a linear transformation like the what you fit is a single vector here or like a single function in the case of a derivative. In the case of a tensor product, you're fitting pairs of vectors. So that's kind of like the difference. But it is the next best thing, that you would do. Like actually, this is like a good example. The determinant is like actually I was going to leave this as an example. I might as well do it here and finish with this. So for example, look at the determinant of a matrix, right? Here, like this is like a useful comparison. Okay, so you look at the determinant, right? So there are a couple of ways to think about a determinant. If you thought that the determinant, right? This is like an interesting case. If you thought that the determinant, what it does is eat a matrix, right? It is an n by n matrix. Okay, the determinant we know is a number, right? Okay, this is not linear because hopefully you remember that the determinant of A plus B is not the determinant of A plus the determinant of B, right? So the determinant of A plus B is not the determinant of A plus the determinant of B, right? So because of that, we cannot think of the determinant as being a linear operation, right? So determinant is not linear operation, right? So far, so good, everyone with me? But what if you said, okay, I will think of the input of the determinant not as being the matrix itself, but just like the n individual columns. Don't think of the determinant as what you feed into it n column vectors, right? So you think of the determinant kind of like you change the domain. So instead of thinking that the domain is a matrix, you think about it as being the n single columns. So I'll write it like this. It would be Rn, I mean, you could write it Cartesian product if you wanted. Like, it doesn't matter. Like, if you haven't seen Cartesian product, all that I'm saying is that now, like that, what you feed into it is kind of like n separate column vectors, right? So, like, I'll call them column vector 1, column vector 2, column vector n, right? And then it produces a determinant of the matrix that you get, by stacking all the column vectors, into a matrix. Then, if you remember the determinant, the properties of determinant is multilinear in this sense, right? Because, like, let me write it on the board. Where do I have my chart? I mean, I'll put like some silly numbers here. If someone asked you to find the determinant of this matrix, one way to do it, if you remember like the determinant properties, is that you could split this column and then you say maybe, oh, this is the determinant of 1, 0, 2. Like I'll keep like 2, 1, 4, let's say. Plus the determinant of 1, 0, 2, and then I keep the x's here, x, negative x, and I have to put a 0, right? And then 3, 1, 1. And so you see like these two columns kind of like add up to the same original ones. And then the properties of the determinant is that you can split it this way, right? So this is saying that one column at a time, you can break the determinant in sums of determinants, right? And so what this is saying is that as a function on two poles of vectors, it is multilinear, like it is linear one column at a time. It's not linear if you add all the columns together, right? So that's why you cannot do it with sums of matrices. But if you just fix your attention on a particular column, there you can break it up. And the same with the scalar, right? Because if you can multiply all the entries here by a scalar, it can pull it out. It's just that if you multiply every entry of the matrix by a scalar, then it does come out with like the number to the power of 20.
And so the determinant itself is not linear, but when we do the determinant operation, columns are growing.
Exactly, yes. So it's kind of like, because it's more like, you can say the word determinant, right? But say the word determinant doesn't specify on what you are acting upon. So if you think of it as acting on n by n matrices as single quantities, then it is nonlinear. But if you think of it as being fed individual column vectors, then it is linear one at a time, and that's why it's called multilinear. And so the determinant is a multilinear operation, and it is in a sense like a tensor. Like, so you would think of it as being a tensor because that's what I was going to get at today. A tensor is just whatever operation is multilinear. So it's a kind of like the generalization. That's why it's a generalization of a matrix, because a matrix is whatever operation is linear. So a tensor is whatever is multilinear. So all that I'm trying to say is that, because of the properties of determinant, this is linear one column at a time, So that makes the determinant multilinear in this sense. So the determinant is a multilinear operation. So you did know a tensor from linear algebra, the determinant, so you just have to kind of like look at it from the right perspective. Linear operation. So that's kind of like that is kind of like closer to the actual definition of a tensor. So a tensor is whatever operation, whatever multilinear operation between vectors, vector spaces or pairs of vector spaces. So in the same way in which a matrix is kind of like a linear operation, so this is related to linear operations. A tensor is related to multilinear operations. And that would be useful, a useful perspective to have throughout the course. But I thought at least I would introduce him now to kind of like get it started, like, because of the useful point of view to that. Okay, so as I was saying, let's finish here because that way I can stick around just talking to anyone who wants to still ask more questions. If you can talk about the that I gave you or whatever else, and that way like I don't want people rush because like some of you do have to leave and then you're gonna stick around for like what we end up discussing. So but yeah, next time I'll kind of like return to this rank stuff and tell you about the singular value decomposition. But let me